Hello, hello. Hi, everyone. Am I audible to you all? Just let me know if I'm audible. Hi, guys. Hello. I think I am audible because it shows here, but just confirm it once and then we'll start. Okay. Thank you, Giga Chad. Okay. So, hi, everyone. My name is Pradyumn, and today we'll discuss the solutions to CodeChef Starters 197, and we'll discuss the first five problems in Division 2. Okay. But before that, we will discuss, I will tell you about our um, CP courses. So if you are someone who is trying to level up in CP, and if you are stuck at solving just one or two problems per contest, our self-paced courses are exactly what you need. We have structured the program into four levels, so that you can start from wherever you are: beginner, pre-intermediate, intermediate, or advanced. You'll learn the most relevant CP concepts through recorded video lectures and followed by carefully curated practice problems combined with guided hints and detailed video solutions that will help you understand the why and not just the how. We believe in helping you build real intuition. If you need more help, you will get instant doubt support from our mentors who are very high rated, so you are never left stuck. And beyond just learning, enjoy leaderboards, gamified progress tracking, internal contests, and PCDs like this one, which keep you motivated and consistent. Pick the level that fits your goals and start learning today. So if you want to know how to choose a level, like which level you should choose, then you can just read the syllabus of these levels, or you can watch this video which explains all the relevant things, or you can even watch the watch the video specific to the course. So for level 1, this video is there which explains the entire thing about the level 1 and so on. So you can do that. All right. So now let's go on and have the PCD now. Okay. So this was the contest, and in Div 2 we'll be solving the first five problems. All right. So first problem was odd prefix sums. You are given an array A of size n. Can the array be rearranged such that all the non-empty prefixes of the array has an odd sum? Formally, does there exist a rearrangement array B of the array A such that B1 plus B2 up to Bi is odd for every I from 1 to n? Output yes if it is possible and no otherwise. Okay, so what they are telling us is that, sorry, we need to determine that, we have been given an array. So let's say A1, A2 up to AN, right? And we have to determine that can we rearrange this array into another array B, B1, B2 up to Bn, such that all of the prefix sums of this B array, that is this prefix sum B1, B1 plus B2, B1 plus B2 plus B3, and so on. Like all of these prefix sums, they all should be odd, right? So is it possible to rearrange that in some order, right? So for example, we have here in the samples like 212. So 212 it is possible because you can just rearrange it and make it 122. Okay. So uh, all right. Let me just, yeah. So sorry, if you make it 122, then if you take the prefix sums, the first prefix sum is 1, then the next one is 3, and this one is 5. So it is fine, right? So it is possible. So this problem is actually pretty simple if you know what happens when you add two odd numbers. Like odd plus odd is even, right? Even plus odd, even plus odd is odd, then odd plus even is odd, and even plus even is even. So like this is some basic stuff. So using just these you can find the answer, because you just want that all the prefixes have to be odd. They have just told you that, like they haven't told you anything about the actual value of that. Like only odd or even you care about that. So you don't actually care about the actual numbers that they are. Like here AI can be from 1 to 100, right? But you don't care about what actually is AI. If you just care about what is AI's parity, that is it odd or is it even, then you can simply observe some things and find the answer. So like, okay, first of all you want the first prefix sum to be odd, right? That means the first element in your array has to be odd. So the first element in your array has to be odd. So this is your prefix sum, and this is your actual array after the rearrangement. So first has to be odd. Then you want the second prefix sum, that is the sum of these two to be odd, right? So if this is odd and you want the sum to be odd, then this has to be even, right? Okay, so this has to be even. Then you want this one to be odd also. So if this is odd and you want to add this number, so you will get this entire prefix. Like if you just take this entire sum which is odd, and if you add this element, then you will get this prefix, third prefix, and that has to be odd. So definitely this has to be even. So following the pattern, you can see that all of these further elements have to be even. Okay, so that's how it has to be. So like what you can do is just bring the first odd element, like just bring the odd element on the front and the rest after that. But for that to be possible, like in the original array you have to have only one odd element. Like you have to have exactly one odd element, right? So in your original array, if you have exactly one odd element, then you can just bring it to the front, and all the rest even elements you will just place them as you want, and in that case the prefix sum will be odd. Okay, so this is pretty simple. I hope you understood. Like I'll just show the code also, and then I'll take the doubts. Yeah, so this is the code. Int n cnn, and then I just take the input of array a, and I count the number of odd numbers. So for int I equal to 0, I less than I plus plus, if ai is odd, then o plus plus, right? So if odd equal to 1, then print yes, otherwise print no. So the code is pretty simple, and I think it should be pretty clear. Yes, Ari, I will be doing that, but it has some prerequisites. At least my solution does. Okay, so I think it should be clear. Split. What is that? Okay, split actually only just binary search on the answer. So little bit of spoiler is there, but yeah. Anyways, so let's move ahead with the second problem, which was this one. So good ranking, pair version. So there are n contestants numbered from 1 to n. Your task is to make them participate in some contests and then manipulate the rankings in a particular way. In each competition, the ranking of the contestants can be considered to be a permutation of the integers 1 to n. That is, there are no ties. A contestant A is said to beat contestant B in a particular contest if A occurs earlier than B in the permutation that denotes the contest ranking. Okay? The following condition should hold. For every pair A comma B such that A is not equal to B, there should exist at least one contest such that A beats B. Your task is to choose the number of rankings, let's say M, and then print M permutations, the rankings of each of the contests. You can have at most 10 contests, so ensure that M is between 1 to 10. Okay. So the only thing tough about this problem is its language. Okay. So what they are saying to us, I'll just explain little briefly. So they are saying that you have to do M contests. Like, okay, you have to make M rank lists of the contest. Like there are N people from 1 to N, and you have to make M rank lists. Rank list means what? Let's say if it is 312, then that means that the person 3 came first, person 1 came second, and person 2 came last or third, right? So person 3 beat person 1 and person 2 in the first contest. Then let's say in the second contest, this was the case, 2 3 1, right? So in that case, person 2 beat person 3 and person 1, and also person 3 beats person 1. So you get the point. So what you have to do is that you have to print M permutations of 1 to N. Like you have to print M contest rankings where you can choose the M. Like it's up to you to print any number of M, like any number from 1 to 10. So you can print any number of permutations from 1 to 10, and it should happen that in at least one of those permutations, A should beat B. A beats B should be there. Like in your output, at least one permutation should be there such that A beats B. And you can print up to 10 permutations, not more than that. So, like, let's say if you printed this, then is it correct? Let's think about that. So, is it correct? Um, so, okay, 1 2 is there, 2 1 is there, 3 1 is there. Okay, 1 3 is not there. So, 1 never beat B. Like, 1 beats 3, 1 beats 3 is never true. So, like, that's why this output is not correct. Okay. So, we have to print up to 10 permutations such that every member beats every member at least once. Okay. So, this is pretty simple. Like, just consider what will happen if I just print this permutation, like 1 2 3 4 up to N. So, if I print this permutation, then which pairs are done? Like I want to make sure that all pairs, like for all pairs A comma B, A beats B should be there. So if I just print this permutation, then which pairs have I sorted? Like sorted, I mean not actual CS wala sorted, but which pairs are satisfied? So in this case, 1 beats 2 is there, 1 beats 3 is there, 1 beats 4 is there, up to 1 beats N. Then 2 also beat 3 in this contest, 2 also beat 4, and so on. So as if you can see, all of those pairs for which A is less than B, all those pairs A comma B for which A is less than B, they all are there in this permutation, right? But all of those pairs for which A is greater than B, they are not there. So if A is greater than B, then A is not beating B for any A and B, right? So what we can just do is print one more permutation, like n minus 1 up to 1, right? So in this case, all of those pairs which have A greater than B, in that case, A beats B is true. So basically, my point is that since you wanted that all possible pairs must be covered in your permutations, so my proposal is just to print two permutations, just print this one and this one, the 1 to n and then n to 1, and all of the pairs A comma B are covered in these two permutations, because if A is less than B, then it is covered in this permutation. Like A will definitely beat B in this contest, and if A is greater than B, then it is covered in this permutation. Okay, and that's how you can just print it. So even though you can print 10 permutations up to 10, but you will just print 2. Okay. So is it clear to you? Shekhar, I'll take this at the end. I mean, like, ideally what you would do is, okay, I think placement season is having some time, right? There is some time in placement season, so you should practice, I guess, lead code and standard DSA problems. Like at this point, practicing CP from code forces is not uh, practical, but yeah. Okay, so this seems clear, and the code, I think it is pretty trivial. Like, just you have to take the input of n and print 1 to n and n to 1. So yeah, we don't have to. No, we don't need to print 10 permutations. Like, even if we did need to print 10 permutations, then we could just print random permutations after that. Like, just print these two, and after that just print random, because your all those pairs gets covered in just those two permutations, and the condition is that all of those pairs have to be covered in at least one permutation. So even if you had to print 10, then just print random. Yes, I am from IIT Roorkee. So yeah, anyways, let us move ahead with this next problem. Okay, so for like n equal to 3, will 3 permutation satisfies the answer? What do you mean, Kavish? What do you mean by 3 perm? Like, for n equal to 3, my answer is 2 permutations. Like, for n equal to 3, I am printing 1, 2, 3 and 3, 2, 1. And like, if any n is 3, then we have 6 pairs. Okay, so 1, 2, 1, 3, 2, 3. Then we have 2, 1, 3, 1, and 3, 2. So if you can see, like, all of these pairs are satisfied. Like, 1 beats 2 in this contest, 1 beats 3 in this contest, 2 beats 3 in this contest, then 2 beats 1 in this contest, 3 beats 1 in this contest, and 3 beats 2 in this contest. So if you just print 2 permutations, all the pairs will be satisfied. Okay, so let's move ahead now. I'll just open this thing. Okay. Yeah, so this is fine, I guess. So let's move ahead with the next problem. So it was split. For a binary string s, define f of s as the longest non-decreasing subsequence of s. For example, f of 0011 is 4 and f of 0101 is 3. So I think they mean the length of longest non-decreasing subsequence, right? So here the length of LIS or LNDS, like, just assume LIS where I means non-decreasing. Okay. So in this case, 0011 is LIS itself. So the longest subsequence is 4, of length 4. And in this case, we can take 0, 0, 1, like this 0 and 0, 1. So we get 3 length, right? You are given a binary string s of length n and an integer k. Consider splitting s into k substrings t1, t2 up to tk such that s is equal to t1 plus t2 plus t3 up to tk. So concatenation operation, that is, like if we concatenate all the ti's, then we have to get s. The score of the score of such a split is defined as the minimum of f of t1, f of t2 up to f of tk. Find the maximum possible score possible by choosing a suitable split. Okay, so this is actually pretty standard pattern, but I will explain to you without assuming anything. Okay, so let's just handle this test case. So let's say we have 10110. Like, I'll first explain the problem. So let's say I have 10110 and k equals to 2. Okay, so that means we have to split this string into two substrings such that the concatenation is the entire string, right? And what we have to do is we have to like maximize the score, maximize the score where the score is the minimum of f of like s1, f of s2 up to f of sk. Like if we split this string s, if we split this string s into s1 plus s2 up to sk, these k strings, where k is 2 in this case, then the score is defined as the minimum of all of these f's, right? And I have to maximize the score. So in this case, how will we split? So actually, in this case, let's say we split like this. Okay, so like one string I have 10 and another I have 110. Okay, so here what is the score of 10? Score of, I mean, what is f of 10? Sorry. So f of 10 is just 1, right? Because either you take this as subsequence or you take this as subsequence. So like the length of lis in this is 1. What about the length of lis in this? So f of 110, I think it is 2, right? Because you can choose this 1 1. Like, okay. So the length of lis is 2. So our final score, if we partition it like this, is minimum of 1 comma 2, which is equal to 1. And like you can verify that for every possible split, the maximum score, like in this case, is 1 only. Like it can always be 1. It can't be more than 1. Okay, so that's why the answer is 1. All right, but okay, now let's think about how do we actually solve this problem. So one insight from after reading the problem should be that what is it asking? Like it is asking that we have to find the maximum possible score, right? Maximum possible score. And what's the score? Score is the minimum of some things. So essentially, we have to find the maximum of minimums. Like we have to find the maximum of minimums. So like the maximum possible value of the minimum of some values. So some of you might know that in this pattern we can actually use binary search on the answer. Okay, so like what we'll try to do is we'll check that for some k, can we make the answer at least k, so greater than equal to k, can we make the answer, that is the answer greater than equal to k. Okay, so okay, we'll answer this problem that can we, or okay, is the answer greater than equal to k. So this is the this is the question that we need to ask ourselves and how to solve it. Okay, like if we have been given some k, then can we find out that is the answer greater than equal to k? Or let's not take k, let's take mid, because k is already used. So I'll just change this. Yeah, so mid here. Yeah, so we have to answer the question that is the answer greater than equal to some value mid, right? And like what is the answer? Answer is basically the minimum of f of s1 comma f of s2 up to f of sk, and we need this to be greater than equal to mid, right? So what does that mean? That means that all of these values all of these values have to be greater than equal to mid, right? Like f of s1 itself has to be greater than equal to mid, then f of s2 also has to be greater than equal to mid, and so on until f of sk it has to be greater than equal to mid, right? And what was f was basically length of lis, right? So what is our purpose now? Our purpose is that we have to check, sorry, we have to check that can we split this string into k substrings such that each one of them has f value greater than equal to mid, right? So how do we do that? Now let us, like I'll show that via an example. Okay, so let's say we have the string 001 001. Okay, 001 001, right? Now let's say we want, like let's say my mid is equal to 2. That means I'm trying to split this into some substrings such that every substring's lis is greater than equal to 2. Okay, so okay, what about the first substring? Like let us just iterate over this string and figure out that what can the first substring be. Okay, so let's say we take this in the first substring. Of course this will definitely be there in the first substring, it cannot be empty. Then okay, currently if I have this substring, then its lis is 1, right? Just 0. Then if I take this 1 0 as well, then its lis is 2. Like this 0 0 is 2. So that means if we just take this substring as our first substring, then we will get our lis as 2, and we needed it to be 2, right? So we will just take this substring as our first one. Okay, so this is our first substring. Now we will choose our second substring. So let's say we choose this one. Okay, so if we have just this one, then the lis is 1, right? So we need more characters. So let's say we choose this 1 0. Now still the lis is just 1, the length of lis, because this is not increasing, right? Or not non decreasing. So for this substring also the length of lis is 1. If we choose one more character, then for this substring like 1 0 0, the length of lis is 2, because we can choose this 0 0. So since we wanted 2, we will again break here, and this is the substring that we have found. And finally this is the last bit, and like we cannot take it as a substring because it will not have the f value or the length of lis as at least 2, so we cannot really take it as a separate. So what we'll do is we'll just merge it into this one only, right? So we have merged it into 1 0 0, and we can do that because the answer for this was 2, right? So if we add one more character, the answer cannot decrease, right? Of course, like if we insert one more element, then our lis can either remain the same or it can increase, right? So I'll just include this into my last, like into my last substring. So essentially what I have done is I have broken this string into two substrings such that each one of them has a length of LIS greater than equal to 2, right? So therefore, okay, and in this case, in this input, my k was equal to 2, right? My k was 2. So like I had to divide it into two substrings. And since I have done that, therefore I can say that my answer, like it is possible to make the answer at least 2. Like it is possible to make the answer 2, right? So the answer is at least 2. Now they are saying that the answer is 3, so that is fine. But that's how I will check that can I make the answer mid or not. So if I generalize this, like let's say I have some string, okay, and I want to divide this into k substrings such that each one of them has an LIS greater than equal to mid. Okay, then I will just iterate over this string. Like let's say I'll try to take this first one, then I'll check its LIS. If its LIS is greater than equal to mid, then I'll stop there and I'll start a new substring from the next index, and so on. Let's say in these three characters we get the mid, so we'll stop there and start the LIS and next. So we will just divide this string into as many substrings as we can. Okay, and if that number of substrings, the number of substrings in which we divided this string, if it is like less than k, like see, we divided this string in as many substrings as we could, right? So if that is still less than k, that means we cannot possibly divide it into k, right? Like for example here, 10110, we wanted to um, divide this string into two substrings. Okay, let's say we have 10110 and we want to divide this into two substrings, and let's say we are checking for mid equals to 2, that can we actually make the answer 2 as 2 or not. So the first substring, what I'll do, I'll take this one, it's the answer is 1 for this. Then I'll take this 10, the answer is still 1. Then I have to take this 101. So this is my first substring which has LIS 2. Then I'll start my substring here 1, then I have 0. So since this one hasn't completed, like even if I take this entire thing, its LIS is still not 2. That's why I'll have to just merge this into the first part. Like I am not able to split these into two. So therefore, since we had to split into two, and like we concluded that there's no way to split into two, that's why we cannot make the answer mid. So our answer is definitely less than mid. On the other hand, let's say we wanted to split this into three substrings. Okay, the problem asked us to split into three substrings, and we are able to split our string into like five. Okay, like let's say this is our string, and we split this into five substrings, and all of the substrings had a f value which was greater than equal to mid. Then I would say that this is a valid configuration because I can just merge these three. Like I can consider all of these three strings to be the one substring. Like let's say just mark this as 3, and definitely I we can say that its LIS will also be greater than equal to mid, because this was greater than equal to mid, right? And adding more characters to it won't make it less than mid. Okay, so that's why if our number of substrings that we could make was greater than equal to k, then we'll say that it is possible to make that answer. Now, one thing that I did not tell you in this is that how do you find the length of LIS? Like while we are iterating over this string, I am saying that okay, this is 10 and its length of LIS is 2. This is one, sorry, 1. Then this is 101, the length of LIS is 2. But how do we actually calculate the length of LIS? Like that's the whole point. Okay. So how do we calculate? How to calculate the length of LIS? for this binary string. So let us say let us solve a simple problem. Like let's say we had been given a binary string. Let's say 1011011101. Okay. And we have to calculate the length of LIS for this. So how do you calculate that? Like how do you write an algorithm? So there might be simpler algorithm out there. Like what I'm about to tell you, उससे भी simpler हो सकता है. It's possible maybe. But what I did was that I just made a prefix DP. Like I just defined that DPI. Like let's say this is index I. Okay. Then DP1 of I. Sorry. DP1 of I denotes the LIS, length of LIS ending at 0. Or basically it is the number of zeros only, right? Like my DP1 of I stores that for this prefix I, what is the length of LIS which is ending in 0. So let's say for this string, the DP1 of I would be 1. Okay. Then for this string, or let's say this string, it would be 2 because this subsequence is there. Okay. So DP1 of I is length of LIS ending in 0. Or I can call it like number of zeros also. Like it is basically number of zeros only. Right. And I'm defining DP2 of I. DP2 of I as the length of LIS ending in 1. Right. Okay. So this is my state. And let's say I want to calculate a DP. Like how do I transition from this? And like DP2 of I is the answer for the prefix I. So until here, if we consider the string, then what is the answer? Right? If we have the subsequence ending in 1. Okay. So let's say we want to calculate the DP. So what is the transition? Okay. Like let's say we know that what is the answer for I minus 1 and we want the answer for I. Okay. So like okay, I think you should remember these. Like I can erase this, right? So yeah, so let's say I want to calculate for this I want to calculate that for this I what's the DP value. So DP1 means ending at 0. So DP1 of I is just the same as DP1 of I minus 1, right? Because this index is 1. So definitely this index is not included in our subsequence because we want the subsequence to end in 0. So if this is 1, then definitely um, I'm not taking this. And if I'm not taking this, then the answer is just same as DP of I minus 1, right? So if the S of I is 1, then DP1 of I is equal to DP1 of I minus 1. And what about DP2? DP2 of I. That means I want the subsequence to end in 1. Okay. So in that case, like either the last character could have been 0. Like either it could be this 0 1, right? Or it could have been 1 1. That is for this previous substring, either we can look at subsequence which ends in 1 or the one which ends in 0, and we can take the bigger one of that. So the max of dp1 of I minus 1 and dp2 of I minus 1. Okay. And just include this one at the end of that. So plus 1 element will be there. So dp2 is this and dp1 is this. If if s of I is equal to 1, and if s of I is equal to 0, then it is simple because in that case the dp2 will be same. dp2 of I will be dp2 of I minus 1, and dp1 of I will be just like, if you want the LIS to end at 0, that means the previous one also has to end at 0. So like you can only append this 0 to a subsequence which has all zeros. So it is just 1 plus dp1 of I minus 1. So like I think I did overcomplicate this. Like there must be a similar solution to this, that how to actually calculate the length of LIS. But if you know how to do the typical LIS problem, then this thinking of this is easier, I believe. So yeah, this was how to calculate the length of LIS while you're iterating over the substring. And like as soon as your dp1 or dp0 becomes equal to mid or greater than equal to mid, then just break that substring on that point. So basically don't transfer the dp values. So like let's say, like I'll show in the code what I mean by that. Like when you are iterating over this string, and let's say your mid is equal to 2 in this case, so you will check this one. Now until here the dp value is just 1, so you will move ahead, then 1 0, it is still 1, then 1 0 1. So in this case your dp2 of I becomes equal to 2. So you will break this substring here, and to do that, just treat this like a base case also. Like just stop here and treat this like a base case. So just initialize this dp1 of I. Like since it is 1, so dp1 will be minus 1, like minus 1, because it is not possible to end in 0, and dp2 will be 1. So like I think I'm pretty clear, but in the core I'll just show. Or do you have some doubts? Like I think this explanation was pretty long, so I will yeah. So RE is telling keep count 0, count 1. We have, when we have 0, count 0 minus minus. I think or you mean plus plus. Else count 1 plus plus, and max length equal to count 0 plus count 1. I mean when you have 0, count 1 minus minus. Yeah, I mean uh, I don't know, like this might be correct, but I have used my thing, and like it is complicated, but do you understand? Like, is there anyone who didn't understand the DP method? Beast, I like right now I'm using it because on Windows my mic is not working, and also okay. So how is f of 0 1 0 1 3? Because f is defined as the length of longest LIS, like length of LIS, right? So 0 1 0 1. इसमें you can choose this 0 1 1. So this 0 1 1 subsequence has length 3, right? Stranger. Okay, I'm assuming you understood. So let's just look at the code. Like you guys might beast. I mean, one more reason is there. Like Windows is pretty intrusive. Like updates aa jate hain at random times, and like Ubuntu is more friendly to you if you are a developer. And like in our some of our courses it's required that we use Ubuntu. Like in our compiler course we have to make a compiler, and for the Linux OS, so for that we have to have Linux. Anyways, let's look at the code just real quick. All right. So yeah, it is pretty complicated, but I mean not really that complicated. It is just annoying to write. So we have nk c in nk and string s c in s. Low equals to 1. So like I am doing a bs on the answer, right? So the answer is at least 1, right? Like of course you can split your string and get the answer as 1. Okay. And the highest answer can be n. So lis can be at most n, right? Now while low is less than high, int mid equal to high less than by 2 and count equal to 0. So this is my check function only. Like I have not made another function, but here I am checking. So count equal to 0. This count is basically that how many substrings have I completed. So like how many substrings have I divided my string into, so that all of them have lis at least mid. Okay. So I have two dps, dp1, dp2. So dp1 means subsequence ending at 0 and dp2 means ending at 1, right? So base case is that dp of 0. So if s of 0 is 1, then dp2 is 1, and if s of 0 is 0, then dp1 is 1. Then just iterate over the string, and we have two cases: if s of I is 1 or if s of I is 0. Okay. So if s of I is 1, then of course dp2. Okay, yeah, then dp1 is dp1 is I minus 1. So dp1 of I will be dp1 of I minus 1. Okay. And dp2 of I can be dp1 of I minus 1 plus 1. And it can also be dp2 of I minus 1 plus 1. But I'm just checking that it has to be valid also. Like dp2 of I minus 1 and dp1 of I minus 1 have to be valid. So like if they're not minus 1, then only I'm doing this. Right. And if s of I is equal to 0, then of course dp2 of I is equal to dp2 of I minus 1. And I'm initializing dp1 of I as 1 because I can of course take that particular character. And also, like I can try to relax it via 1 plus dp1 of I minus 1. So if dp1 of I minus 1 is not equal to minus 1, then I can try to maximize it by, like, I can do dp1 of I equals to 1 plus dp1 of I minus 1. So if you have practiced dp, then this might not be very tough for you. Okay. And then finally, if at current iteration my dp1 equal to mid or dp2 equal to mid, that means I have to stop at this point. Like I have to, this substring is done, so I am incrementing the count of that. And also I am just skipping the next index because that is the base case now. So again, like I'm doing I plus plus, going to the next index and just initializing the base case there. Okay. So automatically I am essentially breaking the string right there. And finally, if like in the current mid, for the current mid value, if we are able to break the string into more than equal to k substrings, then low is equal to mid. Otherwise, high equals to mid minus 1. Okay. So and finally, just print the answer. Since we are doing a base on the answer, we just print low. So if you did not understand this dp part, then you can try this logic. Like someone has written it. Keep count 0, count 1. Like you can try to decipher this. When we have 0, then count 0 minus minus, else count 1 plus plus. Like actually I don't really understand how this worked, but anyways, can't we use bs? So we have length k lis, then I'll be taking 0. If 1 occurs, I'll try to see how many ones are there to the right. If my current length plus number of ones to the right is greater than my mid, but to the right, by like how much to the right you will go, because you need to split the smallest chunks, right? Like let's say we have 0 1 0 0 1. Okay. And your mid is equal to 3. Okay, then what you will do is you will go here. Okay, 0. So find the LIS is 1. Then you have 1. So currently the length is 2 and you have a 1 right here. So you will say that let us just take this entire string, and we have made this increasing subsequence of length 3. But the thing is that you could make it just by taking this also. And here greedily, like, you should take the smallest one. Like, let's say this was the string and you're checking for k equal to, let's say, k equal to 2. Then if you take this substring first, then you will be left with this. And in this substring you cannot take, like, the ls is not 3. So you will say that it is not possible to make mid equal to 3. But actually it is possible, because you can just take uh, these characters and then these characters. So it doesn't work like that. Okay, so if you don't like, if anyone didn't get the DPI idea, then they can alternatively try this idea, which he has written here. Anyways, I'll move on to the next problem. So this is called expected cost. You are on a 1D number line initially at x equals 1. Uh, you want to reach x equals to n plus 1. You can do the following two actions when you are at x: pay a cost of ax and move to x plus 1, or pay a cost of bx and move to a random position among the positions between x equal to 1 up to n plus 1. All of the n plus 1 possibilities are equiprobable. Find the minimum expected cost to reach n plus 1 if we make decisions optimally. Okay, so like, the problem is pretty simple to state. So yeah, so we have a number line. Let's say 1, 2, 3 up to n plus 1. Okay, and we want to reach n plus 1. Currently we are at 1. All right, and now what we can do is either pay a1 coins, like either pay a1 coins and move to this 2, right? Or we can pay a2 coins and we can, sorry, not a2, or we can pay b1 coins and we will move to any random position from 1 to n plus 1. So it might even happen that we are stuck here only. Okay, so we have two options: either we can pay a1 coins and go to 2, or we can pay b1 coins and move to any random position in this entire sequence. And the random position is determined by a coin toss. Like, we can't choose the random position, it is probabilistic, and like every position of out of the n plus 1 positions have equal probability. Okay, so we have to find out the expected value, of, I mean, the expected cost to reach n plus 1 from 1. Okay, so if you look at the samples, then you might be you might think in some non optimal way. So I won't do the samples right away. Before that, like, I'll try to do some mathematics. Okay, so like, actually I'm not really that strong in probability, so I can't really give the intuition here that what's happening, but I can tell you how to solve this problem. Okay, so yeah, let's say we are at 1. Okay, just call like x1. X1 means the cost to move from, or let's say xi, like for any I, xi is the cost to go from I to n plus 1. Okay. So I am defining this term xi, which is the cost to go from I to n plus 1, right? And we want to basically find out the expected value of x1, right? So how do we find that? Now actually we can do it kind of recursively. Like let's say if we are at I, if we are at I, and let's say I want to calculate the expected value of xi. Okay, then I have two options, right? I have two options. One option is that I can pay AI coins. I can pay AI coins, and I'll move to x of I plus 1. I mean, I'll move to I plus 1, right? I'm currently at I, and if I pay AI coins, I'll move to I plus 1. So from there, what's the expected value? It is x of I plus 1, right? So if I am at xi, if I am at I, and I want to calculate xi, then one option is that I pay AI coins, and then I move to I plus 1. And from there, I expect that it will take me x of I plus 1 coins, or like expectation of x of I plus 1 coins, right? So total is AI plus E of x of I plus 1. So like if we choose the first option to move from I to I plus 1, then this is the expected value if we choose the first option, right? And if we choose second option is that we can pay BI coins, and we can land up anywhere from 1 to n plus 1 with equal probability, right? So let's say we landed at 1, then its probability is 1 upon n plus 1, and it will take me even coins to get to my end, right? Then let's say I land at 2, that probability is 1 upon n plus 1, and it will take me e2 coins to get to the end. So, and like I can land anywhere, so 1 upon n plus 1 into e of n plus 1. So like this is your formula for the second case. Like your expected value of xi would be, like if you choose the first move, then it is ai plus e of xi plus 1. And if you choose second move, that just land anywhere randomly, then you will pay bi coins, and with probability 1 upon n plus 1 you will land up at 1, so e1. Okay, and with probability 1 upon n plus 1 you'll land up at point 0.2, so 1 upon n plus 1 into e2, and so on up to 1 upon n plus 1 into e of n plus 1. So e of n plus 1 is just 0, by the way, because that's the definition. Like our definition is the expected number of coins to move from n I to n plus 1. So if you are already at n plus 1, then of course you'll pay 0 coins. All right. So this is your two options. And since they have said that we are taking the move optimally, like if we make the decision optimally, so of course we'll choose the minimum one. Like we will definitely choose the minimum of 1 and 2. Okay. So just to write it a little bit more easily, I am defining f of I. Okay, like f of I is just the expected value of x of I. Like I am defining this f of I, which is the expected value of xi. Okay, so what is my f of I? F of I is just the minimum of ai plus f of I plus 1, comma bi plus 1 upon n plus 1 into the summation of fi over all I. Right? Like what I've written here is the minimum of 1 and 2. Like 1 was ai plus f of I plus 1, and the other option is that we can pay bi coins and land up anywhere. So that's what I had written here, 1 upon n plus 1 into e1 plus 1 upon n plus 1 into e2. So I'm just take out the n plus 1 or 1 upon n plus 1 as common. So 1 upon n plus 1 into f of 1 plus f of 2 plus f of 3 up to f of n plus 1. So this is your formula for f of I. Okay. So until here, do you guys get this? Just let me know that how did I get this formula. And finally, yeah, like f of n plus 1 is 0. Okay. And your f of 1, that's your answer. Like you have to find out f of 1. You have to find out the expected cost from 1, right? And that's f of 1 basically. So yeah, this is your problem. Like this is your formula and you have to calculate that. So Ra Yoshi said yes. Do anyone else has a doubt in this? Like how did we get the formula? I'll repeat that if you want. Okay. So yeah, let's move on from here. So we have to calculate f of 1, right? And our f of I is found by like a of I plus f of I plus 1, like the minimum of these two quantities, right? So the main issue here is that this f of I actually depends on itself. Like you can see this value. In this value, like bi is fine, bi is constant, this is also fine, but in this you have all the values from f of like f of 1 plus f of 2 plus 2 up to f of n plus 1, right? So there is f of I as well in this sequence. So since f of I is depending on itself, that's why we cannot directly calculate it. That's one problem. And another issue is that this f of I depends on I plus 1 also, like the next ones, like the right ones. And it depends on the left ones also, like f1 f2. So like there is no particular order in which we can calculate this. So essentially you can say that this term, this is the term which is causing us harm. I mean, this is the reason, this term is the reason due to which we are not able to calculate our answer. Like let's say we knew the value of this sum. Like let's say that the sum of f of I, if I knew the value of this sum of fi, like let's say it was s. Of course this s is the same for all I. Like the sum of f of I over all I, let's say it is s. If we knew the value of this, then we can easily find out the value of f of I for every I. Like f of n plus 1 is 0, so that is 0. Then f of n would be the minimum of this, like ai plus 0 comma bi plus a constant term. So like we can simply iterate in reverse, because f of I then depends just on f of I plus 1. So we can simply iterate in reverse, like from n plus 1 to 1, and we can calculate this f of I very easily. But that would be if we know the value of s, that what is the sum, right? But the problem is that we don't, right? Problem is that we don't know the sum of f of I, right? But so how do we find this? Like how do we solve this then? The main idea comes here. The main idea here is that let's assume a value of s. Okay, let's assume a value of s and then find out these fi values. Like just find out all of the fi values and then just see what sum you what is the sum that you have right now. So like, let's say you guessed the sum, and then using that guess you calculated all the fi values, and then you calculated the actual sum that you calculated. Like, what I am trying to say is, let's say you guessed that the sum was 10. Let's say n is equal to 4. So we have the points from 1, 2, 3, 4, 5. Let's say you guessed that your sum is 10. Okay, then you calculate that. Let's say f of 5 is 0, of course. Then f of 4 is 1. Like, from your calculation you're calculating, like from this formula you're calculating that what is f of 5. So let's say f of 4 is 1. Then f of 3 is let's say 2. F of 2 is 1.5. F of 1 is 3. Okay, so now, like, you have calculated these values of f. Now what you will do is, you will find the sum of these. So what is the sum of these? 4.5 plus 2 plus 1, which is 7.5. So basically, when you guessed the sum it is 10, then you get the sum 7.5. Like, when you guess that the sum is 10, then the actual sum that you get is 7.5. That means that you guessed the sum too high. Like, this sum was too high. Like, intuitively it makes sense, right? That this guess that you made was too high and you have to go lower. That means that you know that actual sum is less than 10. Like, the actual final sum, the actual sum is less than 10. You know that. So, and let's say you found the sum, like you made this 10 wala guess, and you found the sum, and it came out to be 12.5. Then that means your this guess of 10 is too low, and you have to increase it. So your actual sum, you will know that it is greater than 10, right? So in this way, you will just guess some sum, and you will get the information that was it too high or was it too low. So since you can get this information, you can simply do a binary search on the sum. Okay, so what you will just do is, like, your sum can be from 0 up to, let's say, 10 to the power 18. Like, let's say a very big value. So let's say your sum can be from 0 to 10 to the power 18, right? So you will guess that, let's just take the middle value, which is 5 into 10 to the power 17. So you'll guess this sum. Then if you get that the actual sum is more than that, then your guess is too low, and that will change your active range to this 5e17 to 10 to the power 18. So you can simply do a binary search on your sum, right? And as soon as you converge to a value, like as soon as your range becomes less than 10 to the power minus 6, like they just want the answer accurate to 10 to the power minus 6, right? Like, they are saying that your answer will be considered correct if the relative error does not exceed 10 to the power minus 6. So they want that the precision is 10 to the power minus 6. So as soon as you have the sum in the order of 10 to the power minus 6, like, as soon as your range becomes less than this, like as soon as your r minus l becomes less than equal to 10 to the power minus 6, you will stop. So essentially, you know the sum, correct to 6 decimal places, essentially, right? And then you will just use this sum, and finally one more time you will calculate these f values, and whatever is the value of f1 that you get, that is your final answer. Okay, so like, if I try to show you here, like, let's say 10 2 and 110. Like, actually, showing it doesn't really make any difference. So instead of that, I'll just give a summary of what we did. So first of all, we just derived this formula for our fi. Fi is the minimum of two things. Like, we have two options, and we'll take the better one, obviously. So fi is the minimum of ai plus f of I plus 1, because we can move from I to I plus 1 by paying AI coins, or we can move to a random position. So the other option is bi plus 1 upon n plus 1 into summation of fi. Okay, so this is your formula. And if you knew that what is this sum, then pretty easily you can determine all of the f values, because in that case f of I would only depend on f of I plus 1. And so you will just calculate the f values starting from n plus 1 down to 1, and then your f of 1 would be the answer. But the problem is that you don't know the sum, right? So in that case you will just guess the sum, and you will see that what's the sum that you are getting when you calculate this fi value, right? And if that sum is too less, that means you have guessed too high, and you have to decrease your guess, and otherwise you have to increase your guess. So this way you can do a binary search, and as soon as your range becomes small enough, that is, as soon as you know the sum to a very small boundary, that is a very good accuracy, then you can use that sum to calculate the value of f of 1. All right, that's the entire idea here. Okay, so R.A. Joshi, like, math is not mathing, what do you mean? Yeah, I mean, see, actually, um, the thing is that whatever we have here, like this equation that we have, it is not a formula for finding out the value of f of I. Like this thing here, it is not a formula to find out the value of f of I, because it is circular, right? Like as you said, it is circular. So it's not really a formula to find out f of I, but rather it is an identity in the variables um, f1, f2, up to f of n plus 1. So we have like n plus 1 variables, and we have this identity for all values of I. So we have n plus 1 equations as well. So we have n plus 1 equation, and we have n plus 1 variables. So we have a unique solution of that. So somehow we'll find that unique solution. And like how to do that, how to find out the solution to that, we will just assume this value of s. And like the thing is that we actually assume that it is monotonic. Like when I said that just assume that, let's say the sum is 10, and if you get a smaller sum, then you will decrease your guess. Then this is pretty intuitive only, but you can actually prove it as well. So if you want to prove mathematically, you can simply read the editorial. So like it is actually explained very nicely in that editorial, that how um, yeah, so this is the proof of why it is monotonic. Okay, so you can read this proof if you want, but intuitively I just told you. And like circular dependency is not a problem here, because we are not claiming that this is a formula. Like this thing here, it is not a way to get the value of fi, but rather it is an identity, or it is an equation. We have n plus 1 equations, in these n plus 1 variables. So this system of equation is solvable. And like normally you would take O of n cube time, like using Gauss elimination or something. But in this case, we have a better approach that we can just guess this sum, and numerically we can solve this. Okay. All right. So I'll just show the code for this. Yeah. So we have this code right here. I am doing everything in double. Okay. So I have just stored the AI and BI arrays also in double. So I am taking the input, and low equal to 0, high equal to 10 to the power 18, and an answer. So I'll just do the iterations. So low equal to 0, high equal to 118, mid equals to low plus high by 2. So what I'm searching on is the value of sum. Okay, so the sum can be from 0 to 118, and currently I'm guessing that it is this value right here, the sum of expectations. Okay, and then I'll just calculate the dp values, and like here I just did some optimizations. Like I did not store the entire dp thing, the entire dp array. I just stored the next value. Like if I want to calculate the dpi, like, or f of I just want the value of f of I plus 1, right? So I am just storing f of I plus 1, and also I am storing the sum also, the running sum. So currently f of I plus 1 is 0, like the last value was 0 and sum is 0. Then I'll calculate the value for int I equal to n minus 1, I greater than equal to 0, I minus minus. Current, that is dpi or f of I is equal to minimum of um, next, that is dp of I plus 1 plus ai, comma, sum upon n plus 1, the sum upon n plus 1 plus b of I. So this is my dpi. I'll do sum plus equals to dpi, and I'll update my, like when I'm calculating for I minus 1, I will need this dpi value. So I update this next to cur. So essentially I have just performed some unnecessary space optimizations. It is not like not necessary to do this, but I had just done this. And finally, like I am storing the value of dp1 as well in this ans variable, which is global. Now if sum is less than mid, that means our guess was too high, then guess, so we have to guess lower. So our upper bound becomes mid, otherwise our lower bound becomes mid. And like I do this thing for 100 times, 100 times, because like at each iteration it becomes half, right? The range becomes half. So if you calculate that after 100 times, it will be small enough. Okay. And like it is recommended that when you are doing the binary search with floating points, just do it a fixed number of times. Like don't use while high minus low is less greater than equal to 10 to the power minus 6, because it might give you some floating point errors. And like if you see, like when I used while loop, like here, this is the same code, but I used while loop here, that while high minus low is greater than equal to 10 to the power minus 7, like while my range is very large or it is not small enough, then I will keep doing the binary search. But this was giving TLE. So I think it is giving TLA because it is going into infinite loop because of some floating point errors. Okay. So it is better to just do it a fixed number of times. So 100 times is enough in most cases, because initially your range is of length 10 to the power 18. So if you do it 100 times, then it can get as low as 10 to the power 18 upon 2 to the power 100, which is small enough. Okay. So we do this iteration 100 times, and like on the final iteration, whatever we had the value of dp of 0, we'll print that, because on the final iteration we are assuming that my sum is accurate enough. Like whatever I guessed is accurate enough. Okay. Yeah, I answered this problem. So anything, any doubts, guys? I am counting till 10, or let's say 5. 1, 2, 3, 4, and 5. Okay, thank you. So let's go. Let's move to the next problem. Yeah, counting infinite. For an array A of integers and k a parameter, where ai are from 1 to k, we define f of ak to be the maximum value of L such that a sequence B exists with the following conditions. The length of B is L, um, Bi elements are from 1 to k, and the length of LCS of A and B is less than equal to 1. For certain sequences, there is no maximum value of L. So we define f of a comma k 0 in such cases. For example, f of 1 comma 1 comma 1 is equal to 1 because we can choose b equal to this array, and f of 1 comma 1 is equal to 1 comma 1 comma 2 equals to 0 because we can just choose b having any number of ones. So there is no limit on the number of elements. You are given integers n and k. Count the number of arrays satisfying the following condition modulo this number. So count the number of arrays such that length of a is n and the elements are up to k and its f value is 0. So basically what they are saying is they have defined, like they have given us a value n and k, and we have to find out the number of arrays such that f of a comma k, like we have to find out the number of arrays a such that the f of a comma k is 0. Okay, and a has to be of length n and its elements has to be between 1 to k, right? And what this f of ak is, f of ak is basically, like, let's say you have an array, so 1 2 3, 2 2 3. Okay, so if you want f of ak, then like f of ak is defined to be the length of longest array b, like out of all the arrays b, the length of longest array b such that the LCS, like the longest common subsequence of a and b, is 1. So like here for the example they have given that f of 1 1 comma 1 is equal to 1 because we can choose b as this array, like see here k equal to 1. Sorry, so we can only have the element 1 in our array, and if we choose two elements like 1 comma 1 as our b, then the LCS will become of length 2, right? But we can't have LCS of length more than 1. So like we have to have LCS of length less than equal to 1. So basically, let's say for this array, what is the value of f of a comma k? Like let's say k equal to 3. Okay. Sorry. Yeah. So what I'm saying is, for this array a, what is the value of a comma 3? So I am saying that it is equal to 0. 0 means infinity. Okay. They have defined, like, if the length can be infinity, then define it to be 0. So why can it be infinity? because we can simply take the array b as 1 1 1 1 1, right? We can take it as long as we want, and whatever, like however long we take it, the LCS will be only one length, because I have only a single one in this, right? I have only a single one in this array. So the LCS will be one only, whatever elements we take. So there is no limit on the length of B. So it can go till infinity. And therefore the answer is 0. So f of a comma 3 is 0 for this array A. All right. So that this is the, like, that's what they mean by the problem, that they have given us two integers n and k, and we have to find the length, sorry, we have to find the number of arrays A of length n such that its element is between 1 to k, and also f of a comma k should be equal to 0. That means we should be able to find some b of arbitrary length such that the LCS is less than equal to 1. LCS is less than equal to 1. So like equal to 0, what does that mean? It means that we can find any length b, like whatever length you give me, I can give you an array b of that length such that the LCS of a and b is less than equal to 1. Okay, so we have to find out the number of arrays of a, right? So before finding the number of arrays, a natural question to ask ourselves would be that what arrays a, like when would be, see, we want to count the number of arrays such that f of, like LCS of a comma b, sorry, we want to count the number of arrays such that f of a comma k should be 0. So let's ask ourselves then, when would it be 0? Like when would f of a comma k be equal to 0? So basically I'm asking myself that for what all arrays a can I always choose another array b such that its length can be infinity, and the LCS, like the LCS is less than equal to 1. So for what arrays A can I choose such a B? So one case is pretty simple. Like here, like they told us that f of 1 1 comma 2 is 0. Why? Because we can choose the elements either 1 or 2, and this A has only one, like 1 1, right? Like in this case, my A is sorry, 1 1. So if I choose my b, if I choose my b as 2 2 2 2 2 2 2 and so on, like I can choose any length of b, any number of twos, and the LCS would be 0, right? There is no common element, so LCS would be 0. So if in my array A there are some elements, like see, if this case k is given, then of course we can only choose the elements between 1 to k, right? So if there is any element which is not in the array A, let's say like in this case 2 was not there in the array A, then I could just choose this 2 2 2 2 2 2 2 2, right? Therefore f of A was 0. So f of A is 0 in one case. Like first case is that if any element, or if some element is not present in A, is not present in A, and like between 1 to k, okay, then I can just choose b as x x x x, right? So in that case, f of a comma k would be equal to 0, right? So for all the arrays in which some element is not present, the answer is 0. So for those arrays, the value of f is 0. Now one more case is there. Like let's say we have all the elements, right? So if we don't have sorry, if there's some element which we don't have in the array, then the answer is of course 0. But what if we have all the elements? then in that case, can the answer be 0? That is, can we make b of infinitely long length? Let's ask ourselves that. So if we have all the elements in our array A, then can we always make the LCS less than equal to 1? Yes. Like, just consider an element x which appears only once in the array A. Okay. If x appears only once in the array A, then what we can simply do is again select B as x, 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 and so on. And in that case, the LCS of A and B would be 1. So since we wanted that LCS is less than equal to 1, it is valid. So we can choose this B array of any length. So the length can be up to infinity. And therefore, the f of a comma k in this case would also be 0. So one case we had was that if some element is not present in the array A, then the f of a comma k is 0. And let's say if there is some element which is there only once in the array A, then also f of a comma k is 0, right? So that's fine. But what if we have all the elements at least twice? Like the remaining case is this, right? We have all elements at least twice. Okay. Then I am claiming that in that case, f of a comma k can never be equal to 0. Okay. Like my point is that if every element occurs at least twice, then you cannot take an infinitely long b. It is not possible to make an infinitely long b such that its LCS is equal to 1. And why is that? It is pretty simple. Because let's say, like, my point is that you cannot even make b of length k plus 1. Like, if you try to make b of length k plus 1, and since all the elements of b are in the range 1 to k, right? So if you take k plus 1 elements, then of course at least one would be repeated. So there is some element which would be repeated, right? And we also know that in the array A, every element is there at least twice. So we can just match these with those two elements, and therefore our LCS becomes at least 2. So my point was, you can't even make any b of k plus 1 length, let alone infinite length. So definitely the value of f of a comma k is not equal to 0 if we have all the elements at least twice, right? So in this third case, f of a comma k is not equal to 0, and in the first two cases it is equal to 0, right? So we just have to count the number of arrays satisfying the first two cases, right? Or uh, like, rather than that, what we'll do is we'll count the number of arrays having this case and then we'll subtract it from the total. So like 1, 2, and 3, these three cases exhaust all of the possibilities, right? And only in this third case, our f of a comma k is not equal to 0. So we will count how many arrays are there for this thing, and we'll just subtract it from k to the power n. Like k to the power n is the total number of arrays, right? So we will do k to the power n minus these many numbers. Okay. So now our entire problem boils down to finding out the number of arrays in which from 1 to k, all the elements from 1 to k should appear at least twice, and length is n. So we have to count the number of arrays of length n such that every element from 1 to k appears at least twice, right? So if we have counted that, we can just subtract it from k to the power n, right? And this will be our answer. But this thing to calculate is very a big challenge. Like it is a pretty nice problem to solve this. Actually, it's a bit standard problem, but regardless, it is pretty nice. So I'll explain that in a bit. But before that, I'll just ask if any doubts are there. So anyone who is there until this point in the live stream, do you have any doubts? So like I think R.A. Joshi wanted the explanation of this problem. So I'm assuming that you might be listening to this. So do you have any doubts until this point that we need to count the number of arrays of length n such that every element from 1 to k appears at least twice? I'll take the general doubts after this explanation. Okay, so I'm assuming that there is no doubt until this point. Okay. So yeah, we have to find out the number of arrays of length n such that every element from 1 to k appears at least twice. So first of all, like we have elements 1, 1, 2, 2 up to k k, and they have to be in this array of length n, right? So of course, if my n is not too big, like if n is less than 2k, then of course there are no arrays. Like I cannot have all the elements um, at least twice. If n is less than 2k, then obviously I cannot have all the elements at least twice in this array. So the answer for, like in that case, the answer would just be k to the power n. Okay. So now we have like n is greater than equal to 2k. All right. So we have to calculate that what are the number of arrays of length n such that every element from 1 to k appears at least twice. Okay. Now this problem is pretty good. So I'll try to explain my best, but anyways, let's see. So okay, we have a number k, right? So we want all the elements from 1 to k, that is 1, 2, 3 up to k at least twice. So let's say 1 appears x1 number of times in my array, 2 appears x2 number of times, 3 appears x3 number of times, and k appears xk number of times. Okay, so what do we want? We want that x1 plus x2 plus x3 up to xk should be equal to n, right? And we also want that all of them have to be at least 2. So xi has to be greater than equal to 2, right? So let's say we have kind of this configuration. Then how many possible arrays are possible? Like using these fixed number of numbers, how many different arrays are possible? So essentially we have, like let's say k equal to 3. Essentially let's say we have x1 as 3, x2 as 2, and x3 as 2, and n is 7. So basically we want to find out that in how many ways can we rearrange this array, right? That's the number of arrays having these many configurations, right? So what is that? Like how to rearrange this? Like the number of ways to rearrange this is simply n factorial or like 7 factorial. divided by 3 factorial, because there are 3 ones, 2 factorial and 2 factorial, right? This is what your um, number of arrays having these many elements, right? So somehow if we could just iterate over all the possibilities of this, like over all the possibilities of dividing this n into this x2 x1 up to xk, then we could just calculate their value, like this value, for all the different possibilities and add them up. But that's not possible because there are so many ways to divide this n into these k numbers such that xi is greater than or equal to 2. So we have to do better than that. Okay. So for this, we take help of what's known as generating functions. So generating functions is actually a very like non-intuitive topic. Like if you don't know about already, if you don't know about those functions already, then it is very hard to think about them. Okay. So I'll just try to tell you that what they do. Okay. So let's start with a small example. Okay. Let's say n is equal to 5. Okay. And um, k equal to 2. So this means that I want my x1 plus x2 equal to 5, and x1 has to be x1 has to be greater than equal to 2, and x3 has to be greater than equal to 2. Okay. So essentially what values can I take for x1? Like let's say we can take up to n. Okay. Like of course we cannot take up to n, but just assume for now that the possible values are up to n. Okay. Where n is 3, right? Oh, sorry, n is 5. So we can take x1 anywhere from 2 to 5, and we can take x3 anywhere from 2 to 5. Oh, sorry, x2. We can take x2 anywhere from 2 to 5. And we have to find out the number of pairs such that their sum is equal to 5. Okay. So one pair for x1 x2 is 2 comma 3, right? X1 can be 2, x2 can be 3, and another pair is 3 comma 2. So x1 can be 3, x2 can be 2. So um, we have these two pairs, and you can see that only these two are possible, because if I take 4 comma 1, it is not allowed because it is less than 2, right? But there is one more way to calculate this number 2. Like the answer is 2, right? But there is one more way to calculate this 2. What's that way? So basically you will make a polynomial. Okay. Like don't ask me why, how did I think of this? I did not. It is just um, some genius who thought about this, and I have studied that. Okay. So see, for x1, I can take either 2 or 3 or 4 or 5, right? And for x2 also, I can take either 2 or 3 or 4 or 5. Okay. So basically just make a polynomial. Like for x1, just make this polynomial. Let's say t square plus t cube plus t4 plus t to the power 5. Like this means t square means what? That you are taking 2 for x1. T cube means you are taking 3 for x1. Okay. So this bracket is for x1. Then multiply it by another bracket for x2. So for x2 you can take either 2, or you can take 3, or you can take 4, or you can take 5, right? So this is for x2. Okay. So now if you multiply these two polynomials, and if you find out the power of 5, like if you find out the coefficient of t to the power 5, then my claim is it will give you the number of ways to make 5, right? It is somewhat intuitive. Like, either, like, to make t to the power 5, either we can take t square from this bracket and t cube from this bracket, or one more way is we can take t cube from this bracket and t square from this bracket. So when we open these two brackets, we will get 2 as our coefficient of t to the power 5, and that's how we will know that we have two different ways of distributing this 5 into x1 and x2. Okay, so this is pretty elegant thing, that we can simply make this polynomial and multiply it by this polynomial, and whatever value we get for this t to the power 5, like whatever coefficient we get for t to the power 5, that is our answer. And like, not really our answer, because we are not worried about the number of different arrangements here. Like, what I am simply counting right now is the number of ways to divide it into 2. Like, if I have k equal to 2, that means I can take 1 and 2 only, and my n equal to 5. So there are two ways. Either I can take 3 ones and 2 twos, or I can take 2 ones and 3 twos. So these two ways, like, there are two ways of taking, right? But I'm not counting right now their arrangements. Like, I'm just ignore that for now. Okay, I'm trying to count the number of different configurations. Okay, by not counting the rearrangements. Like, this thing can also be rearranged in 5 factorial upon 3 factorial 2 factorial times, right? So the actual answer is this thing plus the same thing for this, right? That is the number of arrays which have at least two elements of each type. But I am not finding that out right now. I am finding out that how many number of different divisions are possible among x1 and x2. So for that, the answer is 2. And to find that out, we can just multiply these two polynomials, and the power of 5 will give us the answer. Okay, so till here, do you guys get it? Okay, so I'm assuming there's no doubts till now. So yeah, the number of ways to divide this n into x1 x2 xk, like x1 x2 x3 up to xk. Let's say we want to find out the number of ways to divide n into these, such that every x appears at least twice. So x greater than equal to xi greater than equal to 2. So to find that out, I can simply multiply. Like, I can have this polynomial, which is t square plus t cube plus t to the power 4 up to t to the power n, and I can have this multiplied k times for each xi, right? So this is for x1, then again for x2, again for x3, and so on. So basically power k, right? So power k. So whatever is the coefficient of n, coefficient of t to the power n in this polynomial, that will be our number of ways to split n into these x1 x2 up to xk, right? But now this is not over yet, because we have to also account for the rearrangements. Like, as I told you here, that let's say for this n equal to 5 and k equal to 2, we're just counting these two possibilities, that either we have 3 ones and 2 twos, or we have 2 ones and 3 twos. But we are not counting that how many ways are there to rearrange them, right? So how do we account for that? So let's say for some configuration, Like let's say we take x1 amount of ones, x2 amount of twos, and up to xk amount of k's. Then the number of permutations of that, as I told you, is just n factorial upon x1 factorial into x2 factorial up to xk factorial. Okay, right? So how do you like account for this? Because in your answer, different combinations of x1, x2, and xk were there. So you can't really multiply it by some constant value, right? So how do you account for that? Now to do that, there is one more genius method which some genius invented, and I just know about it, which I'll tell you. So my point is that just consider this, like to find out the number of distributions, like the number of divisions among x1, x2, and xk. Um, I said that just calculate the coefficient of t to the power n in this power, like in this polynomial, right? If you want to account for these permutations as well, then just divide by 2 factorial here, 2 factorial here, 3 factorial here, 4 factorial, and here n factorial. So if you do that, and also just multiply the whole thing by n factorial. And now in this polynomial, if you find out the coefficient of t to the power n, then it will give you the actual result. So why is that so? Like I can only give you the intuition. Okay, so I'll explain the example. All right, so let's just take the same example that we had, that n equals to 5 and k equals to 2, right? So we have made this polynomial. Like what I am telling you is to make yeah, t square upon 2 factorial plus t cube upon 3 factorial plus, sorry, t to the power 4 upon 4 factorial plus t to the power 5 upon 5 factorial, and just power k, that is square. And if you find out the coefficient of t to the power n, that is t to the power 5 in this, and multiply it by n factorial, then you'll get your answer. So why is that? Like see, one possibility, like as we saw, there were two possibilities to get t to the power 5, right? So like either you can take, okay, I'll write it differently. I'll write it completely, like power, instead of power of 2, I'll write it like this. So t square by 2 factorial plus t cube by 3 factorial plus t to the power 4 by 4 factorial plus t to the power 5 by 5 factorial. So when you multiply these out, when you multiply these, there are two ways to get t to the power 5, right? Either you will take t square term from here and t cube term from here, right? So in that case, your term will be t to the power 5 upon 2 factorial 3 factorial, right? Or you will take the t cube term from here and t square term from this bracket. So you will have t power 5 upon 3 factorial 2 factorial, right? So these two cases were there. And I also told you to multiply the entire thing by 5 factorial. So just multiply it by 5 factorial, right? So if you see in this, the coefficient of e to the power 5, what did it come? It came out to be 5 factorial upon 2 factorial 3 factorial plus 5 factorial upon 3 factorial 2 factorial. So my point is that you can basically see that the same thing happened which happened in the earlier case. Like earlier we got the answer as 2 because we did not multiply, like, or we did not divide by these 2 factorial 3 factorial and so on. But if you just do that, then automatically it just sets everything, and the coefficient that you will get for t to the power 5, that's actually your actual number of arrangements. So finally, my point is that to answer this question, that how many arrays are there, count the number of arrays such that every element from 1 to k appears at least twice. To find this out, you can simply make a polynomial. You can simply make this polynomial like x square upon 2 factorial plus x cube upon 3 factorial up to x to the power n upon n factorial, and just take its power of k, and whatever you get the coefficient, okay, and multiply it by n factorial, sorry, and whatever the value of, like, whatever is the coefficient of x to the power n that you get, that is your answer. Okay, but the main thing now is how do we actually calculate this. So see, like, one thing is you can calculate in like, first of all, you have to calculate this polynomial, right? And like, actually you can simply just focus on the first n terms. Like, since you want the coefficient of x to the power n, you can simply discard all the terms which are having the power of more than n plus 1. Okay, so at each step, just truncate. Like, what I'm saying is that ideally what would you do? Like, let's say you want to calculate x square plus x cube plus x to the power 4 to the power 3. Like, by hand, let's say you want to calculate this, then you will first multiply these two polynomials, x cube plus x3 plus x to the power 4, x square plus x cube plus x to the power 4, into one more, x square plus x cube plus x to the power 4. So first, what you will do is you will by hand multiply these two brackets, right? These two brackets. So you will get something like x to the power 4 plus I guess, like, x to the power 5 coefficient क्या होगा, 2x to the power 5, right? And x to the power 6 का coefficient क्या होगा, 3x to the power 6 plus 2x to the power 7 plus x to the power 8. So you will get this, and you will have this again, right? And then you will multiply this one and this one, right? But what I'm saying is, if you just want the coefficient of x to the power 4 in this, then these terms are just useless now, because they will contribute to the terms which are more than x to the power 4 power, right? So you can simply just ignore these terms if you just want the coefficient of x to the power 4. Okay, so while multiplying, just only keep track of the powers less than equal to 4. So now you go and multiply this. So in that case, you will get x to the power 6 plus x to the power 7 plus x to the power 8. So this is your final thing. And as you can see, x to the power 4 coefficient is 0. Like, there is no term of x to the power 4 in this. So like, even if you like multiplied this out entirely, like, even if you did not ignore these terms, then also your power of x to the power 4 would turn out to be 0. So this is one way you can optimize your multiplication, right? And another way you can do it is by using this power k. Like, to find power of k, what would you do? You would multiply k times k multiplications, right? But as you might know, you can also do it in O of log k multiplications. How? Just by using binary exponentiation method, right? If you just use bin pow, then you can just do log k multiplications, right? Okay, but now one thing is that to multiply two polynomials of degree n, so I told you that just focus on the polynomials, or just focus on the powers which are less than equal to n, right? So in the worst case, you will have n plus 1 terms, right? x0 up to x to the power n. So in the worst case, you have n plus 1 terms in the first polynomial and n plus 1 term in the second polynomial. and you want to multiply these polynomials, right? So that will take, like, if you naively try to do, it will take O of n square time, right? N square time. To do one multiplication, it will take O of n square time. And you are taking, like, if you are doing O of log k multiplications, So in total, to calculate this polynomial, you will need O of n squared log k time, right? N squared log k. So this will give TLE, right? But what you can do is, like, there's a method to multiply two polynomials of degree n. Like, if you have two polynomials of degree n, then you can multiply them quite easily in n log n time. Like, it is possible. You can multiply these two polynomials in O of n log n time, and that is by using fast Fourier transform. Like, I don't know how it works, but I just know that it can multiply two polynomials in n log n time, or fast Fourier transform or number theoretic transform (NTT). Either one of these, like, they do the same thing. They will multiply two polynomials in O of n log n time. So just by using this, you can solve the entire problem in O of n log n log k. Okay. So in this complexity, you will find out the final polynomial, and it's like the coefficient of n. So, like, the coefficient of x to the power n, you will find out, and that's your answer. Like, I mean, that's not your answer. That is the number of arrays of case 3. Like, that is the number of arrays which are having all elements at least twice. So we will find, like, our actual answer is n to the k to the power n. That is the total number minus that. So just print that thing, right? So that's the entire solution to this. And, like, this entire thing was pretty standard approach. Like, none of this was thought by me. Okay, like, I have done this pattern pretty much earlier as well. That's why I was able to do it. So if you guys have done FFT or NTT, sorry, uh, my health is not very well. So if you guys have learned FFT or NTT, then you definitely must have solved this problem, that how to find out the number of arrays having this condition, right? Yeah. So that's the entire solution for you guys. Sorry. Yeah. So if you have any doubts, then you can try to learn FFT and NTT from some other place, and then retry this problem. Like, okay, if you have any doubts until this point, that how did we come here? Like, I just told you that we have to count the number of arrays which have all the elements at most twice, or at least twice, and just print the k to the power n minus that number. So until that point, it was pretty simple. But to calculate that, it used FFT and NTT, right? So until this point, if you have some doubts, then I can answer you. And, like, there's one more way of solving this. Like, in the editorial, they have given one more way, which uses PIE, principle of inclusion exclusion. Okay, so you can read this editorial from here as well. And the another approach that they have told is generating functions. So, like, I have explained this thing. All right. So yeah, just let me know if you have any doubts. I mean, this was a pretty tough level problem, to be very honest. So some of you, if you are new to CP or even intermediate at CP, then I would recommend you to solve this later when you are more experienced. All right. Okay, so I think you all, like, either you did not get anything at all, or you got it. So either ways, there are no doubts. So I'll end it, I guess. So yeah, this was the PCD, and thank you all for joining in. I'll see you guys next time. Bye everyone.